Hello, good afternoon, everyone. Is everybody able to hear me? Perfect, perfect. Well, thank you all for attending HDC, AIM HDC this year, and then thank you. It's a pleasure to be in front of you guys and share some of my experience. My name is Arun Giri. I'm an Associate Vice President at Union Pacific IT. I head the platform engineering group, and I also had the enterprise architecture and the platform architecture teams in Union Pacific. So I will start. I won't give you. I mean, a lot of you know what Union Pacific does. We're an elder company. We operate in 23 states. We're one of the largest freight carriers in North America. And our journey, like what most people don't see is like, yeah, we're a vital infrastructure to this country, but we're also have a very large, a engineering pedigree. So we're mostly known, like what you'd see from the outside is mostly, big long trains, really cool trains, like someone said, like really loud trains, the big yellow shiny trains on tracks. But what it takes to run that operation is a lot of automation, a lot of engineering, a lot of cool engineering. So I'm fortunate to be part of that team. I've been leading the platform engineering team for many years now, and we've been on a journey to re-platform our core transportation management system for the last 10 years, and we're starting to go live. So the scary thing for anybody who's leading these kind of big efforts is that they say that we don't want to jinx it. We're going to go live. Our just cut over takes a year. So next August 14th is where we're planning to go live. So as we went down this journey of re-platforming our core operating system, we also had to build a very large microservices foundation underneath it. So that journey took several years, lots of lessons learned, and I want to share only a piece of that journey story. And I want to share like what happens when people are doing large-scale microservices implementations, and we had started this journey way before the term microservices even existed in the industry. A few years ago, when we went down this, our board of directors of our company wanted, like, we've been about 8 years into the program, and they're seeing things coming out, but it's a big scary thing. We'd already spent about $300 million on this, and we're building like almost everything is homegrown, and we built a lot of the cool engineering stuff from ground up. And so they got nervous, and they asked us to be audited from outside. So we hired like PricewaterhouseCoopers to come in and audit this whole architecture and the implementation we've done so far. And PwC took about 6 months to audit us. And it's a true story. They actually had to go outside and hire expertise to come back and audit us, because by the time they got into this thing, they figured out that they didn't have the expertise in-house to actually audit and assess this architecture. So I went and hired experts from outside. Long story short, 6 months later, they sent a report to the board saying, in that board report, they said, hey, we had an industry-leading microservices implementation. And so from that day onwards, we started using the word microservices. So it's cool, a good validation that we were on the right path, solving the same problems like all of you all solving hard engineering problems and arriving at pretty much the same solution which the industry arrived at. So without further ado, let's go talk about that experience, right? Like, and let's talk about. Let me set the stage before we jump on, like what is microservice, right? Like there's lots of definitions, but at the core, a microservice is it's a single purpose function, right? Like and it means that it does something, one thing, and we expose that operation over some well-known RPC mechanism, right? Like, I mean, at the core, that's what a microservice is. And so why do we do this, right? Like, since you're on, there's only a few big reasons architecturally why we do this. If you think about, like, well, I mean, it has all the benefits. Like, it's easy to deploy. You know, it's simpler to maintain because these are just building Lego blocks, and you can easily assemble them into other solutions. There's lots of reusability there. If something goes wrong, you can actually detect and fix this, and you can deploy that in isolation, and it's easier to do change management, right? Like you can evolve a single component then instead of evolving a whole monolithic solution base. And if you had to evolve the tech stack underneath one of these components, and let's say that for whatever reason you have to like go to a different tech stack and build this differently or evolve this, or you want to patch it, it's easy. It's easy to evolve that tech stack, and you don't have to do a whole a monolithic upgrade. Okay, so those are like well-known advantages. So what, right? Whenever we start on, like we did too. So I'm not saying anything which we didn't do. We learned a lot of lessons and stumbled and made all kinds of mistakes and refactored millions and millions of lines of code. So trust me when I say that this is not tongue in cheek. This kind of, like, all architecture have some aspiration. If you think about, like, okay, as architects, we always say, well, we know that systems which scale have to be stateless. Absolutely, right? Like, I mean, that's kind of why we built this. There's so much buzz around in the industry around microservices, is because it allows you to scale, and these are stateless components. And we do know that, okay, stateless systems scale horizontally, so that's a good aspiration. It's like we know that we want to handle scale, and so we'll build them statelessly so that we can just add compute nodes and we can just scale them horizontally. Great. Okay, so that works out. And we've read, and instinctively we know, and a lot of industry knowledge backs this and saying, hey, you want to, if you build stateless systems, and you can also end up with loose coupling in your architecture. Tight coupling is bad. We've learned it for many, many years in computer science 101. And then said, great, like it seems like these are all the perfect architectural aspirations, right? Now, and we always imagine our system to kind of look like the one which I have on the screen there, like, a microservice is just hosted on a network connected device, and they all talk to each other, and like there's a user interface which hits that thing through some proxy and middlewares, and okay, great, the world looks perfect from that angle. And that's kind of the mental picture all of us have when we come up with these architectural guidelines, and basically these are aspirations until things start until we start, like, laying down, okay, how do we typically set this up, right? Like, the aspirations aside, all microsystems start like this, right? I mean, if you think about it, the layered architecture never went away, and then so we generally have 4 layers. Like, we have a user experience layer, and it doesn't have to be like a web app, but it can be any experience. There's an experience layer which needs some type of an orchestration layer for non-trivial things, and then that orchestration layer is the one which actually orchestrates, calls out to your microservices API. The reusable part of that API is right here, right? Like, okay, so that's how the world works. I mean, that's how we typically set up. And when we think about this way, we also generally, when we get started, we don't think so much about state management. State management, it means, like, typically it's your transactional state. Like, if you're building a train system or you're building any a shopping system, somewhere you need to have orders and catalogs, and in our case, train schedules, and train objects, and equipments and consists and all that stuff. Like, our business objects. Like that's the state changes is what your service layer is allowing you to go do, and then we persist that state after every successful operation, and we read the previous state, right? I mean, that's, pay attention to that layer all that much when we get started, and therein lies that problem, because state management usually starts out as an afterthought um, until you start scaling your system, until you start scaling this service layer, this layer which is stateless, and it starts going haywire and it becomes this, or at least you think about this way before it becomes this, you have real big problems. This is an actual picture. We built a monitoring solution, like a homegrown monitoring solution, to actually capture to manage and monitor our API platform, like the Microservice API platform, which is replacing our logistics system. That's our transportation control system. And this, if you Google microservices and Death Star pictures, so almost anybody who's done a large scale implementation will have a Death Star picture, and we do too. And it's just ironic that it looks like a Death Star. This is how our monitoring system is actually looks at this when we zoom out all the way up and then look at that all the dots. Like, so each dot there is a microservice, and you can't see all the connections. Like, something reuses on, there's an orchestration, there is a connection between them, and some I've zoomed out enough to show you, and that's how it looks, right? Like, now that's a scary world. That one dot is a microservice. So when you hit this kind of things, and imagine all of this is stateless, like every dot there, and these are non-trivial functions. Like every dot there, it's not doing a simple fetch of one row of one table from a database. Like they're literally, all of them are non-trivial operations. They do something from a business point of view, which has an independent life cycle and does something meaningful. Like, go create me a train, which is one of the most complex operations which we have. Is an API is one of those dots. May not be the most popular dot there, but that's one of the dots. And then so all of that's a setup. So if you think about this, like, when you scale out, the simple architecture, like, which starts out, and when you scale out, the scale introduces, creates problems, and large scale creates really large problems. And that's the kind of the setup for the rest of my talk, and I want to share like our solution to this. So here's another bit of context here. We have, like, there are 5,800 unique dots in that thing. That means, like, if I count up, we have 5,800 APIs in production right now, and we still haven't completely gone live, but that's how much is already in production. So about 60 or 70% of the Death Star is live. This Death Star is live, but as 5,800 of the APIs are already live. We, on this platform, we make about 2.2 billion API calls a day. And so what we had to build out as part of this journey was like, we built everything from ground up, because there was nothing in the industry which actually supported this. Everything from containerization strategies, and we did a very much similar and hosting, which is we did Docker and Kubernetes, like our own version, because Docker and Kubernetes did not exist when we started, and we started hitting scale. But over the years, the service bus and the event bus has evolved, and then so we refactored our homegrown one, and then used like industry components. Like our event bus is built on a Kafka backbone, so that it's scaled out, and we use a lot of open source components to build our service bus, like Zool and Ultra, and then a few of the components and lots of HA proxy, and we proxy all of this, and then so that's kind of our architecture, right? The thing which stands out, that the reason I want to talk to you guys today is this one little place where we had to build a homegrown data store, simply because, like, obviously when we started building this, we had not imagined this Death Star to be this in this shape and this big. But about 5 years ago, we realized that, okay, there was nothing in there. Like, there's no RDBMS or a cluster of RDBMSs which will scale for this. And so we did a a bit of an R&D and then poked around and then looked for industry solutions and people like vendor products, and and we arrived at, okay, well, we could buy one or two components, or but we had to build a data store which scaled with us. Like, the big problem of massive scale microservices implementation is that your stateless layer, when it scales out, your stateful layer also has to scale along with it. And so we had to go build something afforded us to go deep. And then that's kind of the journey, the architecture journey, which I want to share. So how do we scale state in a large scale implementation? Like, what are the challenges? And you would face this, like, since you guys are listening to a microservice talk, I'm thinking either you have an interest in microservices, you're going to do this, or you're already doing it, right? And if you think about, like, somewhere in this spectrum, in this journey, you will hit a problem like this, and this is hopefully a pattern which you can take and implement it yourself. And there's some other products now on the cloud which allows you to do something close to this, but the pattern is important, the design is important. So here's some same kind of stats. Like, okay, so we're very large. We have about 4,600 like synchronous APIs and another 1,200 asynchronous APIs, which we exposed on our platform right now, and so that's massive, right? Like, so a lot of these things are always like, it's easy to so if I think about if I were to oversimplify, and this isn't very oversimplified, I'm just trying to lay out like the problem statement here. If I oversimplify the architecture, there's a layer of software which you can just scale out horizontally, like just add compute nodes. Your service layer will easily scale when you just add compute nodes. Just go on and then you scale out your proxy and your middleware layers, and you can just scale the compute nodes like all day long, right? Like ad nauseum. Like, and you can do either a service mesh architecture or to scale even better. Whatever you do, this layer, it's easy to scale. Like, that problem is solved and that's there, right? You can just deploy your containers all day long on VMs and they'll work, and then as long as you can proxy them correctly and scale your middleware layer. But the real problem though is that persistence layer. I know I put like a database shape in there, so don't imagine just an RDBMS, but any store, like, you to think about this to say, as the scale of your microservices solution becomes larger and bigger and wider, it also means that that layer is very data hungry, because it's stateless. It doesn't remember anything. Like, operations to operation, it doesn't remember anything, right? Typically, this is what happens in a stateless system. I'm oversimplifying this, but generally the pattern, like, it gets a trigger, it gets invoked, right? It gets a trigger with saying, do this action, or I want to do something, right? And then the next step of that service, what it does really is that, okay, I understood what the request is. I need to go get fetch state from somewhere. So it makes a fetch state call to your data layer, right? Like, somewhere it hits that data layer and brings back the state it needs. And then it does the business operation, like all the complex logic, business logic, then it gets executed, married to the state it read from multiple places. And then once that operation, the business logic is done, what does it do? Like, it wants to persist state or tell, like, event out. If it events out in a choreographed implementation, then it has to still persist that state so the next guy can pick up in the chain. And so it's always doing two operations. So for every request it gets to do something, it fetches state and it persists state, right? Like, it's always there. That's the truth for every component, right? And scale that out. Like, if you're scaling the top layer and you almost go, like, you have thousands of APIs like we do, a lot of them will want to do that stuff. Like, it's very few that it doesn't want to, unless it's a data layer API, it does fetch state all the time. And then so the scale at which this scales something here has to scale. So that's because you will do a lot of reads and writes, right? So they have to scale for both read and write. So you can't really optimize for, I'm going to do a lot of reads only. That doesn't work that way, right? Because at every state in your choreography of your microservices implementation, you will end up persisting state. So it has to scale for read and write. And then the second thing is like the thing optimization, you quickly realize like we all will do instinctively, we know that we need to reduce this impedance mismatch. Like my execution layer and then whatever the persistence layer is, like if I reduce that impedance to, if I don't reduce that impedance to a large extent, that cost of will eat you. Like which is required and then over the wire things, and you will never achieve the scale of your microservice implementation. So you quickly realize that you got to figure out how to get rid of that impedance mismatch in that layer. And then like traditionally when we start out, like a lot of us, like including me, you know, we all came from an RDBMS background, right? Like we always never thought about any other, like, you know, 6-7 years ago or even 10 years ago, we never thought about any other data store. Like when we thought about persistence, we thought about an RDBMS. Like, you know, MySQL didn't exist, but let's say MySQL or, you know, Oracle RDBMS or, you know, SQL Server, pick your poison. We always thought about a RDBMS, but that doesn't scale horizontally, right? Like it only scales vertically. No matter what clustering technology you bring, it doesn't work out that way. So, so I'll give you a hint. Like, let's start out think, how do we scale this? If you're on this journey, somewhere in the spectrum of your microservices journey, you got to make a hard choice. The earlier you make this choice, the better it is, right? Because we, in Union Pacific, we paid a heavy price, like because we had to learn this lesson because the industry lesson wasn't there. So we stumbled and scraped our knee and then, you know, broke our nose and, you know, we bled a few times and refactored our systems before we realized, you know what, we got to think about the stateful layer like before it's too late. So nearly for 8-9 months, we kind of ground our development to a halt to go back and rethink the stateful layer. So you got to make some hard design choices upfront, right? Like there's a lot of patterns now in the industry, so you don't have to learn all these lessons. And part of this experience I'm sharing is also sharing that lesson, right? Like, okay, what did we learn, and what solution did we come up? So, what was the design choice, right? Now let's go rethink our design objectives. We know that stateless systems are data hungry, right? Okay, so that's a given. Service chaining is real. Like we will orchestrate something, whether it's a synchronous orchestration or an asynchronous, like a choreography, it will happen, right? Like, so this service chaining is real and you'll end up using both orchestration and choreography. Like there's no system, even though lots of articles and papers are written about, well, you know, the good things about orchestration and the bad things about choreography and you know, or vice versa. It doesn't matter. You'll end up using both because it's different objectives require both these patterns, like either one. So, and I would say that avoid orchestration simply because that doesn't scale as much, but you know, you can't avoid it 100%. So let's think about this from, let's think about it in a fun way. What are the design objectives? All right, so just like any other database would, the first thing you would have to think about is like, don't lose my data. Whatever solution we're going to build, it needs to be somewhat like reliable and fault tolerant. That means it's like basically I'm saying it needs to be ACID compliant, right? Okay, great. Like that's a given. It's a no-brainer. And the second thing you should think about, like the beauty of a microservices architecture is that you don't know how big this will get because you're building so many reusable. If you did this really well, to a large extent, we did that after our second and third try, is that we have lots of reusable building blocks, right? Like the more reusable building blocks you have, your business will want to go and take advantages, and you will come up with a lot more creative business applications on top. That means that you don't know exactly how big this will get, and you'll get a lot bigger, just like ours. And we always want to be like your design objective is like, I want that layer which manages my state to scale. Like I just want the comfort to just add some nodes, just like I can do on my stateless layer, and it should work for the stateful layer, right? That's your desired business object, design object. Let's take the and then the next three are kind of like wishful thinking, but it gets really, really important at large scale. Like, why is that? Like, we don't want to code for every change, correct? Like, we want to choose. We know as our business objectives evolve, as our systems, like we're on a 10-year journey, so we could have never hoped for a models not changing, the concepts not changing, right? Like that's a given. So upfront, you have to think about like, how am I going to manage the models, the business context models change and support that change like forever, right? And obviously, like, you know what, like just writing cruddy code to do like boilerplate stuff to go get data from a database and back and forth, like, you know, like ORM mapping and stuff, like, okay, that's boilerplate stuff. Like, we don't want to pay programmers for that thing, right? Like, we're too expensive to go do that stuff. And so automate that layer away. Like, you know, the data access should be as simple as like, I know where like that model exists, like the business context object exists. I just want it. Like, it should be as simple as it should be in your native language as of doing like calling and invoking an API, right? Like, it should be that simple. And you also need, I mean, since we started like with the relational database years ago as our backing model, and we know that, okay, at some point, like we did a, you know, informal study, and 60 or 70% of our code was just built to do like, go fetch me, like join a bunch of tables and then fetch me this, and then, you know, do like kind of an ORM match and say, oh, this thing is I need to convert this big blob of record set which comes back into this expensive object tree, right? And then vice versa when we store it back. That's all we did, right? Like, think about that. 60 or 70% of your code is just cruddy code. Like, you don't need that, right? It needs to go away. All right. So let me mix in, like, that seems like a very good desire for any data layer solutions. Like, there's a few other things which we had. We knew that, okay, we had to write lots of data. And the thing about for us is like, it needed to be really fast, right? Like, you saw our Dead Star picture. All of that thing that they're starting to do, and I'm doing, you know, 2 billion transactions, like API calls on that thing. That platform has to support at best the same layer, like, of scale. And it needs to be really fast. Otherwise, you will grind these orchestrations to a halt, right? So it needs to be really. And then high throughput was a native requirement, like, and it has to be really high. So we don't know what that number is, but we knew that it had to get really huge. All right, so what else did we have? We knew, we'd experimented, like, as we started moving away from RDBMSs and said, you know what, my data layer can be anything other than an RDBMS, can also be an RDBMS, but can be other things. We have on our data layer plan, we went to the model of, hey, some problems require me to have HBase as a solution, like on a Hadoop-based solution. Some layers requires a graph database maybe, and then some layers requires you know, Postgres. Like, you pick your poison, right? Because there were different solutions we had to bring to bear simply because, like, you know, that fit the use case. Now, when we started looking at this, like, there were too many proprietary APIs. They brought, like, a lot of them. Everything which we brought in was open source after the Oracle RDBMS, but there were lots of proprietary. The interfaces, it's not an industry. There's no JDBC around on top of them, which abstracts me from data access, or there's no JPA strategy there. Like, all of them had their own native interfaces. So while that becomes unmanageable, we quickly realized, like, okay, that's not going to work out either. And then we also needed, like, you know, if you think about system of records, like, hey, if, like, one of the core operations we do is to go create a train, like a virtual train, like the train which is running physically has a digital twin in our system, right? Has to, like that, we are a planning system. And and that means like whenever a state changes, like whenever we detected the real train moved and the digital twin said, oh, I moved, like I had to do some business logic and say that this state of this train changed, it had the event out. That means it had to tell other people who are in the choreography ecosystem to say that, hey, the train moved, or the train had a conscious change, or whatever the business operation, the business state changes are for that object. The only way you could actually do a choreography is that we needed events to come out, like that state change events, and that should not be an explicit programming interface. Like we don't want the service layer programmer to remember to go event out that, oh yeah, I changed the state of this train. Oh, now I also need to send out an event on the event bus. What we decided quickly is that, okay, that layer, that responsibility can be pushed down to the data layer, because it's the only one. It knows for sure that it actually wrote down that value, that object, that state of that object. It knows, it's the only one which knows it. And then so we have to figure out, how do we do that? Like, okay, so there's a lot of databases in which are cloud native. I was listening to a session earlier today, HDC, about CosmoDB, which seems to do something like this natively. So that's an industry requirement. Like you end up in a large scale implementation and you want to choreograph and kind of do an EDA, event-driven architecture on top of this. You want that native event to come from your data layer, like natively. It's like and so you want to be able to configure that. So those were our requirements. So I'm going to introduce you, like there's a lot of words in here, but I'm going to give you a gist of this, like since this is getting recorded, and you will have this, like you can always refer to this later. We introduce a word cache. Okay, it's kind of overloaded term, but think of a cache as a complete domain model. For us, the train, that was one of the most complex objects we have in our ecosystem is a train. And it's not a very simple 10 attribute thing. A relational database equivalent of that thing was a 26 table join. If I were to get back one train object, I have to join about 26 tables and then bring back that data structure back. And then we create this object model called a train. So it's big. So what we decided, like, okay, so what if we just cache the post join concept? And we're not using an RDBMS. I'm just using this as to illustrate the story. Like we cache that. That's the domain object. That's the domain object which can be passed on. What if we cache that thing? What if we didn't want to explode into a third normal form and then kind of reassemble this on the way back? What if we just hung on to that thing and allowed some operations to occur on it? So that was the thought. So a cache is nothing but a complete domain model, right? And it's about just one thing, staying true to our microservice principle. A cache, it holds only one domain model and one type of object, and that's it, right? And we said, like, once you think about this, a lot of things become really simple. Like the parent on a cache, you can only have one get API on it. Like just go get me a train. Like it should be as simple as go get me a train, right? Go get me a car. Go get me like a consist and things like that, like which are like business friendly names, but it gives you that stateful object. And then most people would think we all come from SQL background, like so we want to find me all the trains which are like which have an origin of Council Bluffs, right? Like that's a legit question the business layer can ask, the app layer can ask. And so you want to return like n number of train objects, right? Like kind of imagine the where clause of your SQL, and like you want to be able to do that. So we said, hey, on a cache, we want as many find APIs as we could deploy. And so we kind of said, if you can implement this pattern, so it's a very generic set of like rules in a pattern, or a pattern, and that's what a domain model caching is. Like cache the whole model, like means that whatever is your single transactional context and that's what you want, and just imagine that you have a cache, right? And then you have one GET API, one save API, one delete API. It's because these are about one single thing. And then you can have as many finds as you want, right? So that's great. That seems to work out as conceptually, right? So what we ended up doing, we took that and we built a layer of abstraction and a whole bunch of software, right? And last check, okay, so we wrote about 250,000 lines of code. We built a custom database, like a highly scalable implementation of domain model caching, the pattern which I just described. And it does all of this, and we said, hey, the whole implementation is, in order to implement this, we'll expose these 4 APIs, and that's all it has. Like every cache has only these 4 APIs, and then you can have as many finds exposed, but there's only 4 APIs, and that's the exact signature. Now, it simplified the world a lot for us, right? So what we did was, like, we built kind of a REST layer on top of an abstract data store, right? Now, it's a very high level conceptual, like everything which is in green is what we had to build. The component which we used was, it's open source now from Oracle, Coherence. When we purchased this, the company was still, Oracle had not bought that company. So it was from Tangasol. And so it evolved, Oracle bought it. And so Coherence is an in-memory data grid. So we took an in-memory data grid for in-memory data grids are at a very simplistic level. What it does is it takes it can make the heap of one of your JVMs and combine it with a whole bunch of other things and provide you a clear abstraction hiding you. Like, it just allows you to just store and scale out your JVM heaps as a data store, right? Like, and it has a layer of API on top of this, abstracts this. And so you could just, as long as you could distribute the JVMs and then put them on different servers and spin them up, and your data lives in that heap, and you're accessing these objects right from the JVM heap. And heap management and some networking magic is what that Coherence brought to the table. And then we took that and we built a whole database around it using the concepts which I said in our domain model caching implementation. We built an orchestration layer, a mediator layer, like, which does all these translation and mapping and protocol translations. The thing which we had to build out, like, it took us about two plus years to build, is all of the bottom things. Like, we had to build a lot of things which a database really has, like automatic, data loss detection. Since now these are like distributed on multiple servers, in order for us to bring all of the reliability principles I laid out, like, don't lose my data, right? You have to plan for things dying, things fail. Like, in a distributed computing world, you have to assume that everything will fail, and it will fail at some point or the other. But the one thing which is guaranteed is it'll fail. And so when you have things which you're expecting it to fail, you have to make sure that handling failures is a mainline feature. And means that there are nodes, like, even though there's enough replication, there's no single point that there's only one JVM which holds on to this. We have multiple copies, and this is an oversimplified architecture picture. And we also have enough intelligence built in there to target different racks. Like, so we don't put the same JVM with the same shard on a server which is on the same rack. Look, we're kind of rack safe. And then we also do site safe. That means that the second copy, this server actually lives in another data center, and we do real-time replication between these. So we had to build a lot of guarantees in there. And it took us a while to get it right. And there's different implementations now, but in order for you to do implement this domain model caching implementation, at least for us, we had to solve all of these engineering problems. And we had to build this up, database recovery and automatic recovery. So when nodes go offline and they come back on, they join the cluster, And in cases like, let's say I had a big catastrophic failure and we lost one complete data center, and if you still lose it, we quickly, the cluster automatically organizes the data into a what we call, a get it to rack safe mode. It means that, hey, I can get it into distribute this thing automatically into other servers, which is in this data center A, which is still alive, but make sure that, okay, it's not on the same rack, because the rack can become a single point of failure, like all servers in rack can go on. And even if I lose half of those, it will still move the data into it'll go away. At that point, it just becomes machine safe. I got your copies, 2 copies on 2 different machines, 2 different servers, but I can't guarantee that they're on different racks. And so we had to build a lot of these kind of mechanisms, and that's what we built. And even if you build all the safety, horrible things happen, right? Like things die. And when things die, so we have like a data loss prevention and a detector. Like we know there's enough facilities which Coherence gives you on the wire. Like we can listen to network events and then say, hey, I have a partition loss event. That means that at some point Coherence gives up and said, I lost too many nodes and I can't talk to my other buddy. So I'm going to tell you, I broadcast on the network, like on either on this little island which it's created itself, like, hey, I lost partitions. Like, and then at that point, you don't want your business layer to get wrong answers. So our loss prevention, what it does, it actually shuts down all of the front door. That's why we have that API abstraction, that the web service mediation layer automatically shuts down. And then the recovery agents wake up, and then they see that, can we recover this from persistent store? So every time we're doing these write operations in memory, there's in the back, like we make sure that, okay, it's in 2 copies in data center, and then we're also asynchronously writing to a physical store at the same moment. There's probably a few milliseconds or microseconds where, like, if everything blew up, I could lose things, but there's no database on the planet which actually guarantees you that SLA anyway, so it doesn't matter. We guarantee to the level that any database on this planet will do too. And so once you reach that level, it recovers automatically. And then we go to the backing store. If I can talk to it, we recover, and we reload all the partitions in the available nodes in the cluster if we can, and only then the doors open automatically. So as far as our clients go, they get meaningful HTTP errors. In many cases, the grid layer automatically tells them on the service bus that, hey, service not available, or other meaningful errors. We never give a 404. Like we try not to give it for unless we completely died and everything blew up. And so the app layers have lots of guarantees and different SLAs. So that's what it takes. The domain model caching implementation does not need this implementation. I'm just saying, in order for us to marry that domain model caching implementation to actually make it robust and make our system of record for a core transportation system work, we had to go build this one. All right. So just on that shield layer, like, which is what we call our database shield, scalable, highly available, like horizontally scalable, enterprise integrated, enterprise ready, low latency database. That's what shield. We had to come up with a backronym, and so we came up with one. So we have, this is kind of our current stats. We have about 213 caches. It means they're, like, think of them as like database instances. That's what underneath our Death Star. We have 213 discrete databases, and all of them scale horizontally. These 213 are spread about, and don't ask me why it's an odd number there, because there are a few of them are management servers, right? And there are about 120 servers is what holds the giant hypervisor size servers, not piddly ones, and they spread on 2 data centers. That's our implementation, and we currently hold in production about 3 terabytes just in RAM, like in just heap space, like without replication. Like if you add all the applications and the 2 data centers, it's 4 times that, and so that's how much data we hold in heap on this implementation. So we put all our eggs in this basket, and the the pattern we've used is a domain model caching implementation. So I'm coming to the end of this thing, and so I'll be happy to take questions after these last 2 slides. Like, why do we do this? Because it's singularly the most important thing we could have done. Like, this is a company's crown jewels, or replatforming of our core transportation system. So we didn't take this lightly that we had to go build one of these. But we couldn't buy our way out of this. We bought a component, like Oracle Coherence is a component we bought, but there was no implementation, and there is nothing which is close to what we need even today. I mean, there's some cloud providers who have some of their proprietary databases that way, but then I lose control, right, over this, and then it's company's crown jewels, and so we had to build this, and no matter what you guys do in your microservices journey, as you get bigger, you have to, at least currently as it stands, the technology as it stands, you don't have to build everything which we built. If you implement this pattern, which you have to at some point, you will have to just build some parts of this thing anywhere, right? And our challenges were unique, but we couldn't avoid building this, so we have to build this. So I'll leave you guys with like one last thing. It sounds like a sage advice, but it's something which is coming from more humility than just bravado here. It's that it's really hard to go do this. It's a big part of this is proving to yourself that this will all work, which it does, which you can, but the outcome is really worth it, because but a few things which you have to do is that start with the why. Like, if you can't answer the why, if the reason is not valid, it means that you never think that this is going to scale. You don't have to do this because it sounds cool. Hard engineering problems are really appealing to engineers like us, but don't do it if you can't answer that question. If you want to build a highly available and system like this, it comes with cost and complexity, and a huge engineering cost, and you'll have to sustain this implementation for a very long time, and so it's costly. So it's not for the faint of heart. So don't do this because we want to engineer things. And there's a couple of big paradigm changes. It's different from an RDBMS, right? And then so just caching objects, like it's not a true object store, but caching objects comes with a set of paradigms which you have to experience and you learn if you do this. And then you need different kind of, there's no such thing as like DBAs who actually maintain that layer. You need actually proper data engineers who are actually also very good, in our case, have to also be good Java architects, right? Like, and so there's a set of things which changes, like when you start down this journey and then you want to go replace your data layer and make it scale, right? So that's my last thing. That's my last message. And then so I'll be happy to take questions, either via chat, I'll stay along, or if you guys want to jump in and ask me questions. So Aaron or Matt, how many more minutes do I have? Or am I almost out of time?
About 5.
About 5 minutes?
Yep. Can you hear me now?
For some reason, I can't hear Aaron, so
yep.
We have that issue. If you guys have questions, if you don't mind, just type on the chat session. Since you guys can hear me speak, I will speak out the answer, or I'll just hang out after this too. And then if you guys have other questions and if you want to ask me outside of this session, I'll be happy to answer this too. So otherwise, well, thank you for giving me the opportunity to speak to you guys, and I hope this talk was worth it, and you guys got something out of this one. Well, thank you guys.
For those of you, I have put the survey link in there. Please don't.
Okay, so, well, thank you, Nate. if you were starting at step 1, what would you do differently? Okay, so let me keep that question. So, all right, so if I were to start this today, the few things we would do is that the tech stack has evolved. Okay, so 2 things I would do. One, I wish that we had actually figured out this domain model caching pattern sooner instead of stumbling. What we learned is that we validated by doing this that this pattern is kind of what the industry is also recommending. They're talking a lot about hey, your microservices having a different bounded context, having a model tied to your bounded context, not necessarily kind of the DDD argument, but your bounded context being like, where are your transactional boundaries, like API boundaries within like a set of orchestrations, and that's the models you need to go cache, right? Like, and that's the microservice data stores. And so we know that, okay, wish we were smart enough to go figure that one out first. The second thing is there are enough tech stack. The tech stack has evolved. So I would, you could take the implementation pattern and say what pieces already exist in the marketplace, and I would start there. Like, but the implementation literally has to have all of these properties. All right, so I didn't read all the questions, so obviously I probably skipped through something. Do you think you can shell Vibo? All right, yes, as a product. Well, that's kind of the intent, that it would be happy to go talk about, commercializing that as a product. If you can reach out to me and like ask me that question, like, okay, I mean, we do have, Union Pacific has a commercial entity, like we fully own one of the subsidiaries we have is called PST, and through that we actually do our own software shells, like things which we engineer under the UP brand. We don't sell under the UP paper, we sell it under the PST brand, and then so we'd be happy to collaborate or share or think of commercial ideas. All right, I got a couple more minutes, I guess, left. All right, so Aaron, did you catch anything else which I might have missed? It was probably questions which got.
There's one. There's one at the
You gotta
bottom.
type that question. What were some of the challenges with mirroring or data integrity? The concerns being so distributed. That's a good question. So that took a while for us to engineer and then get over. So replication. So there's two types of replications. Like one is like you can do a stretch replications. We've quickly figured out that when we stretch the cluster, like a cache being a whole set of JVM, think of this as a cluster of JVMs. When we stretch that cluster across data centers, one, you can end up creating an island quickly. So we needed to build and this is a peer-to-peer a network, like which it creates, like current creates, and then so when one data center goes away, you can end up creating islands, and you can have transactions running on both. And then so we had to go work around like how do we prevent this, and so we built a layer, transaction coordinator using Zookeeper to figure out which was inactive. And we also said that we will never stretch the cache as a cluster across data centers. What we did was we created 2 independent clusters and we replicated across them. Like, and then so there was always one which is targeted as primary, it took all the load. So it obviously increased the footprint of servers we needed, like the compute doubled simply because of this, but it guaranteed that the data integrity to a level that otherwise we couldn't have guaranteed. So it prevents silence. We replicate, so any write happening on cluster A, which is primary, is guaranteed. The client only gets a response back if we could write it to the other data center if it's alive. So we did that kind of the mirroring ourselves. Can I make my slides available? Sure. I have to get a yes from corporate relations, and then I'm sure they will say yes, and then I will Erin or I'll just send it to one of you guys, since I work with Azel or you. Would it go on the AIM site, Erin? Since I can't hear you. What are real-time challenges faced during database shield layer? So we have to get using the cloud into the data center. So I'll answer both questions, like the better scalability for you. For scalability, yes. Can I auto scale this? So we have to build some of the auto scaling ourselves inside. So this is built, it's agnostic of our UP data center. So that layer, we can actually go run this on the cloud, and it's kind of the idea that as we are evolving, and a lot of our footprint is also becoming like, hey, we need to end up with a hybrid cloud infrastructure. So yes, the second question, like, yes, we can actually do that, because we built some of the auto scaling inside already, and we can take advantage of what the cloud providers do. The real-time challenges are latency, right? So you have to think about the targeting your client experience, keeping the latency really, really low. So we have, like, for every data access service, which we have hundreds of them, we have, like, in our SLO, we tell our client like what the best we could do. So on an average, it's always less than 50 milliseconds. Like, and these are not trivial things. The objects which go back on the wire back to the client, like, pretty big. Like, a train is one of the largest objects we have, and then so we guarantee that, you know, an SLO, when we put that, and then we have built enough monitoring to detect that if we're missing our SLOs, then we might have to scale and do all that stuff. They're asking if we could likely made public in some way. Sure. I'll work with AIM to figure out, or I'll put it on my LinkedIn. So you guys have access. I mean, there's a LinkedIn link to my profile. I'll put it there. All right. Well, thank you very much. I hope this thing was useful. Aaron, do I just hang out here if other people have questions, or what do you want me to do? Oh, okay. I'll hang out for 2-3 minutes, and I'll see if, like, lots of people are leaving, so obviously we're all going to the main stage. But feel free to reach out to me on LinkedIn, and I'll be happy to answer all the questions. All right. Thank you, guys. Take care. Bye-bye.
Thank you, everyone.